All right. So a couple of things I want to point out before you get going. So I put up a folder under the Files tab. It's got 2 practice exams as well as answer keys. One of them I have like it's the answers because I kind of worked through it and have more detailed answer key. I will try to get up a detailed answer key for that other practice exam as well. I just can't put an exact time on it. Hopefully it'll happen at some point this week, but I don't know exactly when I'll get kind of the free time to be able to sit down and kind of put that together. But I'll try to get a detailed answer key to practice exam A up this week as well. And then kind of it also has some files that, whether or not it's Word or the PDF, they're the same thing. But for whatever reason, like I said, sometimes in the web browser especially, this Word document looks all goofy and it's got lines going across it. So just in case you have a computer or a web browser that's not compatible, it's the same formula sheet just as a PDF. So we won't have that exam until next Wednesday, but kind of as we're getting closer to it, those materials are there to kind of prepare. All right. I also put all the old lecture slides in this folder where kind of notice you'll have the skeletons, but then also kind of the completed versions. So that's another good resource going into that exam. Any iClicker questions, so any slide that says iClicker, those completed versions will also have kind of what the answer was, right? The skeleton slides that I post, I leave out what the answers are. Otherwise, what's the point in me asking you that question in class, right? Other than that, I think that covers everything. So before we kind of jump into material today, are there any questions for me before we get going? Yeah.
You said you're going to go back and make assignment to get credit for this particular question.
Yeah, so for number 14, or what was it? Yeah, I haven't done that for you guys yet, but yeah, I have to go back in since the due date's passed. I'm going to go in and add the credit for that. So I think it was number 14. If I remember correctly.
11, 12.
Part B on 11 and 12. And yep. Yeah, I'll go through those and kind of get that added in. Maybe after class today, if not, for sure tomorrow. Any other questions for me before we kind of... All right. So we left off talking about these Bayes examples where sometimes I might be interested in, given that I see a certain outcome on the test, what's the probability that the true state of nature is, whatever it is, right? Whatever the context of the example is. So the equation we had for this looks something like this. I'm just going to write it out. We had it last class, but just so we have a point of reference as we start working on these examples. We've got the second group here. Okay. So we're going to kind of do another couple examples with Bayes' theorem before we jump into the next, kind of, sort of the last thing we're going to talk about before the exam. But let's say maybe the setup we have now is, instead of like last class, we're using like HIV positive, HIV negative, and then seeing either positive or negative on the test. Let's kind of do a goofy, it'll seem goofy at first, and I'll try to make it like connect with a real world application. But let's say our society has decided that we're okay, a truth serum has been invented, and we're okay using it to try to identify who's guilty and not guilty of certain crimes. Okay? So this truth serum works pretty good, but it's not perfect. So the two states of nature we have are that someone's either innocent or they're guilty. And then the outcome of the test is the truth serum either makes them say they're innocent or they're guilty. So we've got states of nature. We have 2 outcomes of the test. We are giving these following probabilities, right? So given that someone's innocent, this truth serum makes them incorrectly say they're guilty 1% of the time, or probably 0.01. Excuse me, given that someone's guilty, the probability the truth serum makes them actually not confess, or right, say that they're still innocent would be 10% of the time, probably 0.1. Okay? We're then told that out of all the suspects that are brought in, 5% of them are guilty. Okay, and this is where my grammar mistakes might be a little bit confusing. So I'm going to change this to here. I'm going to actually oops. No, the suspects are guilty if the truth serum, right? So the original slides didn't had it said a little bit differently, but I'm going to try to make it a little more clear. So really this is saying that underlying state of nature that someone actually is guilty of a crime, that probability is 0.05. Okay? So then if the truth serum indicates guilty, so given this specific outcome of the test, then what's the probability the person is actually innocent? Okay? So we could go ahead and solve this, but I didn't really walk through, I don't think, kind of showing you guys the tree, or at least I can show you a different example that maybe will help make a little more sense. And some people like these probability trees, so right here. So let's say this example, right? I've got kind of two different states of nature, two different sides of this tree. So the first is the probability that someone is actually guilty. Right? The other is that probability that they're innocent. Right? Those are my two states of nature. I want to think about it as S1 and S2. I can do that. So I know that if I have these two states of nature, they're essentially like complements. Those probabilities of the states of nature always add up to 1. That was one of the setups we had for these base theorem problems. So if I'm told that the probability that a suspect is guilty is 0.05, what's the probability that they're innocent? I'm either guilty or I'm not, so they have to add up to 1, so 0.95. However, I can then start to think about, well, on each branch, right, I usually have these conditional probabilities that I'm told. Sometimes I'm only told one of them, but when I'm told one, I indirectly know another conditional probability. So what we're going to do is think about, and I'll move out of the way here in a second. So we're going to have two probabilities. Make sure I give myself enough room here. What we're going to do is condition them both on the same state of nature of whatever side we're on. So here, I'm going to condition this on that the individual is guilty. So given that they're guilty, I can only see two outcomes from this truth serum. Either the truth serum makes them say, I'm going to shorthand the word guilty with a G here. So either the truth serum makes them say they're guilty, or it makes them say they're innocent, right? Those are the only two outcomes I can see for the test. So was I given one of these? Which one do I have? Guilty. All right, so given that they're guilty, the probability that the truth serum makes them say they're innocent is actually 0.1, right? So given that they're guilty, the probability the truth serum makes them say they're innocent, 0.1. Well, if I condition on that same thing, right, that they are guilty, what's the probability the truth serum makes someone who's actually guilty say they're guilty? All right, well, I know that if I condition on the same state of nature, the probability of the two outcomes of the test have to add up to 1, or if they're on the same branch here, on that same level, those two would have to add up to 1. I would then do the same thing over here. Think about how I can do this without running out of room. By the way, here, just a second. So we'll go. Okay. So over here, I'll now condition on the other state of nature. So that the person is actually innocent is what I'm going to be conditioning on. And then the conditional probabilities I'm going to have are still for the outcomes of the test. So given that they're innocent, what's the probability the truth serum makes them say they're innocent? And given that they're innocent, what's the probability the truth serum makes them actually say they're guilty? Well, I have one of these probabilities, right? Given that someone's innocent, the probability the truth serum makes them say they're guilty is 0.01, which then, given that someone's innocent, conditioning on the same state of nature, the probability the truth serum makes them say they're innocent would actually just be 0.99. I have the same tree, conditioning on the same state of nature on this side. So the two outcomes of the test, those conditional probabilities will add up to 1. So now, no matter what question I'm asked, I have all the probabilities I need to answer. Okay. Now, I might not need all of them, right? Because what I'm actually doing here, what I actually am going to try to find, I'm going to write this out in the context of our example. Okay? What we have is if the truth serum indicates guilty. So if the truth serum indicates guilty, what's the probability the person is actually innocent, right? That's what we're looking for. Okay? So our S1 is that the individual is innocent. Our outcome of the test, our E, is that the truth serum makes them say they're guilty. Okay? So what I would do is essentially write out the general form of the equation everywhere where I have everywhere where I have S1, this first state of nature I'm interested in, I put the word innocent. Everywhere where I see E, I put truth serum is equal to guilty. And then what would my S2 or my second state of nature be here? S1 is that they're innocent. S2 would just be they're guilty. Right? So I would just use that general form of the equation. Once I write out the conditional probability I'm looking for, now it's just a matter of writing this out in the context of my example. Okay? I mean, you don't have to do that. If you can like visualize wherever there's an S1, you would have the word innocent. That's fine. But I think it's really helpful to just write it out in the context of your example. Okay? So here, we identified all the probabilities we were given, and then we actually identified a few more that we were given indirectly. Yeah.
Just in the first equation, is it given E S1 equals, or is it given S1 E equals?
Given S1. Hold on.
Like just in our first equation up top.
Right here?
Yeah.
So this is given E. Okay. What's the probability of S1, right?
Okay.
The thing that we're given to be true is what's on the right-hand side of that vertical line. Yep. Any other questions? Sorry, I jumped the gun there without asking. Okay, so we identified what we were given and then some additional stuff as well, which might end up being helpful. We defined the probability of what we were looking for. Here I shorthanded a little bit more on the slides, right? But I is innocent, G is guilty. I then could write that formula out in the context of my example, right? If I don't want to use I and G, I could write out innocent and guilty, write the whole word if I want to, right? But now it's just a matter of plugging things in, right? What's the probability that someone's innocent? 0.95, right? So I just go 0.95, 0.95. What's the probability someone's guilty there? We had that was 0.05. So I can plug this in. Given that someone's innocent, what's the probability the truth serum makes them say they're guilty? Well, we actually directly given that, which was 0.01. We also had it in our tree, right? So I can plug everything in that I was given directly, but there's going to be one component that I'm missing, right? So given that they're guilty, what's the probability the truth serum makes them say they're guilty? We weren't directly given that originally in this previous slide. However, we had the probability that given someone's guilty, the truth serum makes them say they're innocent with a probability of 0.1. So we automatically know that if we condition on that same state of nature, the conditional probability for the other outcome of the test, those would have to add up to 1. So we know that that's going to be 0.9. Right, so we found that in the tree. That's why I said if we do this ahead of time, we'll always have the information that we need, right? So then it would just be a matter of kind of figuring out what that other conditional probability is that we weren't directly given if we hadn't already set this tree. Yeah.
You wrote it up there for the S1 given E.
Yep.
Is that switched?
Nice. Did I write something backwards here?
I think the E and the S1 are the extended formula.
Oh. No, you're right. I wrote it backwards here, didn't I? So this should be E given S2. E. Thanks for saying something. I'm human too, so I definitely can make mistakes. Yeah, right. Here's the conditional probability I want, so I'm gonna have to use like the reverse conditional probability to find that. Yep. Any other questions at this point? Sorry if that was confusing having that up there, but now like once we have the actual correct general form of the equation, right, then it's just matching up our E and our S and writing out in the context of our example. So, in this one, it's a good example of if I had done all of this work ahead of time, I'd have those missing pieces. I don't have to do that, right? Once I get to this point and I'm stuck, I can look and say, okay, from this conditional probability, I can figure out the other outcome of the test when I'm conditioning the same state of nature. Really, whatever you're more comfortable with. When it comes to the exam, you're asked a couple questions over like the similar set of things. Probably makes sense to just go ahead and like figure out all those probabilities ahead of time. That way you don't kind of get tripped up when you're missing something later on. Okay. Any other questions on here? So we plug in that missing piece and we get about 0.174. Okay. So really another thing I want to point out here, and I think I did this last class, but I want to reiterate this. So what I'm trying to find is that given the truth serum makes someone say they're guilty, the probability they're actually innocent is 0.174, right? So 17% of the people that would be in jail if we administered this truth serum would actually be innocent. Let's think about what that numerator and denominator kind of represent, though. Right? Maybe it helps if I go back and have the formula written out here as well. So this numerator, right, behind every probability, right, we start with some frequency, right? So this is kind of like the people who are innocent, but the truth serum made them say they're guilty. Right? So that numerator is going to be kind of like our people in jail who are innocent, but the truth serum made them say they're guilty. So it's almost like you have the frequency of innocent people who the truth serum made them say they're guilty, right? So the original probability of what we're looking for was given the truth serum made someone say they're guilty, what's the probability they're actually innocent? So ideally what I could do is take the number of people who confess and are actually innocent and just divide it by the total number of people who the truth serum made them say they're guilty. But the people that the truth serum made them say they're guilty is really composed of two individuals. Some of them will be innocent. So the frequency of innocent people who the truth serum made them say they're guilty. And then the other individuals who will have confessed are guilty people who truth serum made them say they're guilty. So it's like your denominator is always composed of two groups, right? It's the same outcome of the test, but right, some of those people will be one state of nature and some will be the other. Right? So this kind of gives me like my new denominator. Before, my denominator was just everybody, right? No matter the state of nature, no matter the outcome of the test. But now that I've conditioned on that, the truth serum made them say they're guilty, it's like my new base is not everyone, but just this limited number of people who have confessed, the truth serum made them confess or say they're guilty. Now, those individuals, that the group that I'm conditioning on, is composed of people who are actually guilty and are actually innocent. So if I can find those two frequencies, I would add them together. And then to know the probability of those people who confess to the crime, who's actually innocent, I would kind of put the number of innocent people who confess to the crime in there in my data. So all of that's kind of floating around behind the scenes of these probabilities. There really are frequencies, right? And we talked about last class, sometimes you get this counterintuitive result, especially like with the HIV example where, look, if the probability that you're innocent is relatively high, even if the truth serum isn't, making some people, a lot of people incorrectly confess, that's still going to be a large number of people, right? This truth serum is pretty accurate. Right? It only has like false positives or people who confess to the crime but actually are innocent, only 1% of the time. But 1% of the majority of the suspects, right? 95% of suspects, that's going to be a pretty large number, right? So even if we have pretty accurate tests or pretty accurate truth serum here, we're still going to end up with something like 17% of people who were in jail, right? The truth serum makes them say they're guilty, are actually innocent. Any questions on this before we kind of keep moving here? So hopefully, right, there's no questions. That means that we could solve this question. Right? So we have the exact same setup, but now I'm interested in, given that the truth serum indicates guilty, what's the probability that the person actually is guilty? Right? So we're going to be conditioning on an outcome of the test, right? That the truth serum makes them say they're guilty. But now we want to know what's the probability that they are actually guilty. So I'll give you a couple minutes to work on that. Feel free to work with the people next to you, talk with people around you. Probably give you about 3.5 minutes or so, and we'll kind of come together and talk about this. Okay. All right, so we can use the general form of the equation, identify what we're looking for, write it out in the context of your example, and then kind of plug in the probabilities that we kind of identified earlier into that Bayes theorem equation once you've written it out in the context of your example. So, see you guys working on it. It's not, give it some alarms the closer you can. There's still quite a few people missing there. So I'll give you an added benefit for not just being here. It's good for you to be here and see what this works, but what's also going to kind of just get some key points. So, leaving it open, I'm going to kind of talk about it a little bit, so hopefully everyone's made this one correct. So, I basically will follow the same thing that I did in the previous problem, right? The only thing difference is now I'm conditioning on the same outcome of the test, right? But now I'm interested in what's the probability that the person actually is guilty. Okay? So the state of nature I'm interested in is basically just reversed. So what should I do next at this point? Once I've identified what probability I'm looking for, what will be the next step? So all you just respond right away, so you know what the next step is. What would be the next step, right? Yeah.
Probably write out our formula over here.
Yeah, right. Take this general form of the equation and write it out in the context of our example. Right? So once we have that written out in the context of our example, we should have had all the probabilities that we needed to plug in, right? So it would look something like, oh, I don't even want to go back. It would look something like this, right? Where we had this written out, using guilty, true serum makes you say you're guilty, right? We can then plug in all those probabilities that we originally identified. Like we identified those together earlier. It's the same, right? I didn't change any of those values. It's the same values as before, right? It's just be a matter of plugging those in. Once we have those plugged in, whoops, right? Then it was just a matter of getting those numbers into our calculator. Okay? So, is there any part of that process, like what was kind of tripping you up the most, if you had to say? Yeah.
Finding which numbers went in which pieces of the formula.
Piece of the formula. So that for sure, if didn't write down what we had earlier, that's what would be a lot more difficult. And for this one, right? Go back. I gave it to you in the microphone. Yeah, there we go. Right. So we've got at least two conditional probabilities here that weren't even given to us in words. They were just directly given to us, right? Now, there may not be, one of them I might have to kind of find the complementary conditional probability to it, right? And that would be kind of building out that tree, but the tree should have been exactly what we had before. Right? I kind of even made sure to remind you that the probability that someone's guilty, just that underlying state of nature, is 0.05, which means the probability they're innocent is 0.95. Right? And so a lot of it probably does come down to like making sure initially you write out the probabilities that you're given and like kind of keep those at the top as you're working on the problems so that you always have those to go back to as a reference. Okay. But there's actually a much easier way to solve this one. Now it's something we haven't talked about really yet, but it's really similar to something we talked about. So here we found, given that someone is, the true serum makes them say they're guilty, we found the probability that they're actually innocent in the previous example was 0.174, right? So if I'm just looking at these, what do you think that given the true serum makes them say they're guilty, conditioning on the same outcome of the test, but looking for the probability now that not that they're innocent, but that they are in fact guilty, what do you think these two conditional probabilities likely add up to? 1, right? It's a little bit different than what we were doing before, because before we were conditioning on the same state of nature and looking at the outcome, two different outcomes of the test, right? Well, now it's a similar idea. If I'm just conditioning on the people that the true serum makes them say they're guilty, it's like I start with my room of all my suspects. I administer this true serum. The ones that it makes them say they're guilty, I remove them and put them in a different room. Now that I'm only looking at people that the true serum made them say they're guilty, of those people, what's the probability that they're innocent? 0.17. So the probability they're guilty would just be 1 minus that, right? They're either guilty or they are innocent, right? Once I've conditioned on the same thing, it's almost like I've reset my entire experimental outcome space down to this smaller space, right? But now I'm ignoring all the other possible outcomes. I'm only interested in this new space, which then if we're dealing with probabilities, like that space might as well be 1, right? Because now that I'm saying I'm only looking at people who the true serum made them say they're guilty, that's like my new denominator, my new base, right? So I could have just subtracted this from 1, do what, 0.826 there, right? Now, if I went ahead and wrote the equation out in the context of my example and plugged in my probabilities correctly, I would still arrive at that same answer, right? In fact, it's going to be this exact same equation because my base is going to be the same. It's all the people that the true serum made them say they're guilty. It's just that now, of that base, I'm not interested in the people who are actually innocent. Now I'm interested in the people who are actually guilty. So my denominator will look the same. It's just that now the second part of my denominator would be my numerator. Right? The part on top is the number of people who are guilty and the true serum made them say they're guilty. So if you wrote this out, you should have the exact same denominators you did before. These two would likely be flipped in order. And then your numerator would just be that second row. Does that make sense why we can do this? It's the same idea as when we condition on the same state of nature. If there's two states of nature or two outcomes of the test, it doesn't matter if we're conditioning on the same state of nature and looking at the two outcomes of the test, or we're conditioning on the same outcome of the test and looking at the conditional probability of the two states of nature. Right? Either way, those two conditional probabilities would have to add up to 1, as long as we're conditioning on the same thing. Okay? Questions on this one? There's only 23 of us here. I thought I counted a few more. Make sure you actually get your response. And I left this open and I've given you the answer. So hopefully everyone gets this one right? Everyone got an answer in? I might have counted wrong. All right, 23 of us here. Okay. So we just went through that. So, this truth theorem kind of seems like a stupid example. Right, there's a great application or a corollary to real world, which is that instead of a truth theorem, just replace that word with jury, right? The jury finds you guilty or the jury finds you innocent. And there is an actual true state of nature. You actually are innocent or you are guilty, right? So you can actually find these types of conditional probabilities, right? Given that someone's guilty, what's the probability a jury finds them innocent? Or given that they're innocent, what's the probability the jury finds them guilty? We can get an idea about these things by going back at historical court cases and looking at cases that got overturned after the invention of the use of DNA evidence, because we could actually see, okay, these cases, the person actually was guilty, but at the time the jury found him innocent. Or at the time the person actually was innocent, but at the time the jury found them guilty. Right? So we can look at these kind of reversal cases like that. The Innocence Project is one, not company, but a corporation or not-for-profit that does this. Right? We can go back and look at some of that old case reversal data and get an idea about what these probabilities are. Then we might want to know, okay, given that someone's in prison, or that the jury found them guilty, what's the probability that they are actually innocent? Use Bayes' theorem, write this out in the context of our example. These conditional probabilities we can kind of get from all these cases that have been overturned or kind of finding out that someone was actually guilty after the fact, even though they were found innocent by a jury. Or we can kind of look at historical, the probability that someone's actually innocent or guilty. It's probably a little bit harder to get real good data on that, but we could kind of use different values and kind of come up with a range of probabilities here that we might expect that given that a jury finds someone guilty, what's the probability they're actually innocent. That range would be kind of, well, the probability basically that you're wrongly convicted, right? So I had what, given that you're guilty, the jury finds you innocent. Given that you're innocent, the jury finds you guilty, right? I guess I used this in one of my other sections, like nobody knew what this documentary was. I guess it's getting aged at this point. But if you haven't watched Making a Murder, you're doing yourself a disservice. You should wait. I'm thinking it's still out on Netflix. It's great. Anyways, I digress. So pretty, real world application for using this Bayes theorem. And we basically follow the same kind of pattern that we did with these other problems. Okay. All right. So kind of wraps up Bayes theorem stuff. We should be able to get through general discrete random variables today. I'll probably start us out in the binomial, just in case I kind of forget at the end. And I will post an announcement about this once I get back to my office, but I will be putting up kind of one of those videos that I expect you watch before class on Wednesday. It covers the next type of discrete random variable we'll be talking about on Wednesday. We won't start that one today. It's called the Poisson, so we'll kind of walk through kind of the basics of that. But before we get there, we have to talk just about random variables in general. So a lot of this is going to look kind of like review. It's something similar, very similar to something we've already done. So we're looking at a random variable, not just a variable in our data set. It's going to be that a random variable is something that we can record the outcome of, but it's an experiment that hasn't been run yet. So it's still like a projection about future outcomes. We don't actually have the recorded data, but it's going to be something that's going to happen that we then can record the data for. Okay? So this will make a little more sense, I think, once we start looking through some examples. But we're also going to be interested in numerical responses, right? This random variable will have some numerical responses. So just like before, we've got two different types of quantitative variables, discrete and continuous. We won't be doing anything with continuous random variables before the exam. So a couple of these slides I'm actually going to gloss over because we're not doing anything before the exam with continuous random variables. We're going to only be focused on these discrete random variables. Okay? So that's, helpful. The way that we're going to notate these discrete random variables is this capital letter X. Right? So we're always going to identify something as a random variable or that the outcome hasn't occurred yet using this capital X. Now, the different outcomes we can see X take on, right? X1, X2, X3, and we're going to give some actual values here. So this might be like if I ask someone the number of people in your household, right? That capital X could take on the value of 1, 2, 3, 4, all the way up to whatever the largest family size is, right? So if I'm asking someone, I don't know what their response is going to be yet for the number of people in their household, but I know it's going to be somewhere between 1 and whatever the largest family ever has been. Right? So now that I've got all these different possible outcomes, okay? Like I said, X1, X2, X3 will be some actual values, right? I'm thinking about, it has to, usually with a discrete random variable, the reason why it's they're easier to deal with is it's usually a small set or a finite set of values, right? It's not like open-ended, it doesn't go off to infinity, although sometimes it does, and we'll actually talk about how we deal with that. But usually it's a small number of responses, and so it's a little bit easier for us to deal with. That's why I introduced discrete random variables first. Okay? So we've already looked at this before, but right, discrete means we'll see integer values, but we can't see kind of the decimal values in between. Okay? So that's kind of a review. Like how many days a week did you do something? The number of people in a household. I've got some other examples. We'll skip continuous for today. Family size, I kind of use this one, right? Or the number of dependents, or that's going to be discrete. Something like distance would be more continuous, right? We can actually measure this out to whatever decimal we want. And then one thing that's also kind of interesting I wanted to bring up here is we started dealing with these discrete random variables. And it's kind of like, well, we skipped all the qualitative stuff, right? But we actually didn't, because what we can do is convert, for lack of a better word, convert a qualitative variable to be discrete. How do we do that? Well, if we ask somebody, do you own, what's your pet ownership status, I guess? No pet, dogs only, cats only, both cats and dogs. That's a qualitative response that I would be recording, or that I would actually see the outcome be. But we can just give every single qualitative response an assigned numerical value, right? So now when I'm thinking about the random variable of pet ownership, right, it takes on these different qualitative responses, but I can just code those as 1, 2, 3, and 4 and say, okay, the probability that someone doesn't own a pet would mean the probability X is equal to 1. So we can convert qualitative variables into quantitative variables kind of just by assigning those different outcomes that we could see with numbers, right? You typically starting at 1 and just kind of progressing. Right? So that would be kind of a nice example where we turn a qualitative variable into a discrete random variable. Yeah. So we'll get a couple of definitional things out of the way, and we'll actually start working on some problems here. So just like we did frequency distributions for a variable where we actually had recorded responses already, we can do a probability distribution for the different outcomes that we could see and their associated probabilities. Okay. So we could put them in a graph, a table, a function. So imagine before, before when we had frequency distributions, right, which was that first Excel assignment, which to be fully transparent. So I have my GA help me grade those. But a lot of times it's like, have them grade the stuff that I know that like you can follow a template of. If he has any questions about anything someone did, he gives those to me and then I grade those. Right. So if it's something a little bit, errors were made that aren't quite as common or something, yours might not get graded until he's done with all of them. Gives me the ones that he wasn't sure how to grade, and I kind of complete those. Okay. So you'll start seeing those grades pop up here throughout the next couple of days. But that was a frequency distribution, right, where we would create kind of this histogram using this bar chart. We can do a very similar thing. So if we're thinking about the number of people in a household, so 1, 2, 3, all the way up, basically what we're going to do is now, instead of looking at the relative frequency and graphing that as our y variable, Well, we haven't actually run this, we haven't asked the person how many people in the household yet, but we know based off historical data, maybe the probabilities associated with each of these outcomes, right, is a little bit different. So ultimately, it's going to look almost identical to what we were doing with relative frequencies and graphing those as kind of our histogram. But it's just the different possible outcomes in the future and their associated probabilities. So this probability distribution we can show in a table. Quite often, we're going to actually have a function that would give us this distribution. So hopefully by the end of class today, we talk a little bit about the binomial distribution. We'll kind of continue our discussion next class on that. And that has an actual function that gives us the probability of seeing different x values. So if we think about this probability mass function, we'll write it kind of capital P of x. It's kind of just like if you would write a normal function. I don't know how long it's been since you guys have taken a math class, but right, sometimes you write f of x, or this function when the input is x. Same kind of idea here. We'll input different values for this random variable, and this probability mass function spits back out at us the probability we see that value for x. So you can imagine we'll have all these different values x could be. So for the number of people in the household, 1, 2, 3, 4, 5, up to 20 or whatever the highest value is. And then for each one of those outcomes, we'll have the associated probability. We could then take those x and y pairs and kind of graph them out, right? Put them in a nice kind of column or bar chart. Now, this probability mass function, remember, it's spitting back out at us a probability. So it still has to follow the same rules that probabilities have to follow. It's somewhere between 0 and 1. At the highest, it's 1. At the lowest, it's 0. Probably not going to see those very often. Sometimes we'll see zeros. Never really 1. Those aren't interesting examples. And then just like relative frequencies, I'm taking every possible outcome and I add up those probabilities. They're always going to add up to 1. Similar to when we said with relative frequencies, that represented the relative frequency of every possible outcome. So we said the relative frequency should always add up to 1. Think about it this way. If I ask someone the number of people in their household, and I take the probability that they respond with 1, plus the probability they respond with 2, plus the probability they respond with 3, all the way up to whatever the highest number of people in the household is, well, that covers every single possible thing I could ever see them respond with. Those probabilities should add up to 1, right? Or 100% of the possible outcomes like this. Questions on that idea before we continue? So like I said, it's like a lot of this stuff is like very synonymous with what we were doing with relative frequencies. And that's because relative frequencies really just represented probabilities. In fact, the way we assign these probabilities, quite often, unless it's a very specific type of distribution, usually we're using historical data and empirically assigning the probabilities. And what are those probabilities? We're using the relative frequencies as our probabilities. So they really are the same thing. It's just that we're projecting for the future now. So we talk about it in a slightly different way. Instead of using the relative frequencies, we call it like the probability something happens. So it hasn't occurred yet. So just like with relative frequencies, we can do cumulative, right? So we have cumulative relative frequencies. We can do a cumulative mass function. The probability x is equal to this value or anything below it. So one thing that's kind of nice with these discrete random variable examples is if I think about this cumulative mass function, so let's use that number of household example. And let's say I ask you, what's the probability that there are 3 or fewer people in the household? Well, there's either there's 3 people in the household, or there's only 2 people in the household, or there's only 1 person in the household, right? So if I'm saying I can only ever see exactly 1 or exactly 2 people in the household, essentially they're mutually exclusive of x. Now what this is saying is, what's the probability x is equal to 3 or 2 or 1? We're looking at unions there. So remember we said when we wanted the union of 2 events, that was take the probability of each event and subtract the intersection. Well, if these are mutually exclusive, the intersection is 0, we essentially can ignore it. Okay? So here I'm saying what's the probability it's 1 or 2 or 3, looking for the unions of these different outcomes. It essentially just becomes what's the probability x is equal to 3 plus the probability x is equal to 2 plus the probability x is equal to 1. That's as low as you can, 0 or negative. I guess you could have 0 people. Then were you asking how many people are in the household, right? So we're kind of assuming there's at least one person in this household being surveyed. So finding this like cumulative idea is just basically start the probability of the highest number in that range and add up the probability of every value below that. Right? So if we're looking at really high values of x, what is this cumulative mass function going to be close to? All right, so if I think about here in the context of our example, what's the probability that there are 20 or fewer people in the household? That probability is very high x value in the context of our example. This probability should be really close to what? 1, right? I mean, just intuitively, what's the probability if you ask somebody how many people in their household and it's 20 people or fewer? I mean, I would think it's exactly 1. Who the hell has more than 20 people in their household, right? And that's huge, right? So, I mean, there might be some people I probably shouldn't say like that. It's a good thing. People are good. I have a big family. I love big family. I have a big family. But I'm just saying, like 20 is a lot of people, right? So, as we get to really high values of x, that cumulative mass function is close to 1. If I get to really low values of x, my cumulative mass function starts to get pretty close to 0. So not anything wildly new. So what I could do is take some existing data, think about if I didn't have a specific function, but I was just given the probability. So here I've got the number of new hires that a company had in the last 35 years, right? So this is, I guess, an interesting company, right? There was never a year in which they had 0 hires. A couple of years where they only had 1 year where they had 2 new hires. Looks like the most common number of hires they have every year is 3 or 4. There were 7 years where they hired 3 people, 7 years where they hired 4 people, and they've never hired double digits. Right? So we've got all these different possible outcomes for this x value. Now, based off the historical data, we might want to project how many people do they hire next year. So I've got my frequencies here. I've got my number of hires. How can I start to empirically assign these probabilities? Or how can I create the probability mass function? So how can I turn those frequencies into probabilities? Simply divide them by 35. Total number of observations, right? We did that last class in the Excel example where we built our own contingency table. You can convert frequencies to probabilities by simply dividing by your total number of observations, which you can get here by just adding up the frequencies, right? And I also told you this last 35 years. So that was, that we were looking at 35 years here. So once I've converted those frequencies into probabilities, these are the probabilities I'm going to use to make projections about the number of new hires the next year, right? Something that hasn't happened yet. Okay? And hopefully these probabilities add up to 1, right? If I've done everything correctly. That was the idea that we look across every possible outcome, right? Add up those probabilities, they should always add up to 1. Any questions on any of this before we keep moving? Okay. So I could plot those in a graph. I kind of already showed you with the number of people in a household, the idea behind that, right? And it kind of conveys to me the same information that those frequency distributions do, right? The most likely outcomes I'm going to see next year are 3 and 4. Looks like these are fairly likely outcomes, maybe seeing 7, but probably I see 10 or higher. It's not going to happen. I mean, based off the historical data, there's no likelihood of me seeing double-digit hires this next year. So if I've got all this, right, how might I come up with what I would call like the expected number of hires this next year? So the expected number of hires, you could also think about is actually going to be, based off historical data, the mean number of hires. Right? So if I want to find the mean of a discrete random variable, or here the mean number of new hires, I don't want to simply add these values up and divide by the number of values I have, like a typical mean, because I know that some of these outcomes are way more likely to occur than others. So I want to weight the outcomes that are more likely. So what can I use maybe as my weights here? What's telling me how likely or unlikely these outcomes are to occur? The probability of them occurring. It's literally like the definition of probability. So I can use my probabilities as weights. So I'm kind of jumping the gun to one slide here, but I want to show you this. So if I'm looking for the mean of a discrete random variable, a lot of the times we'll write this as the expected value of that random variable, right? But it's really representing a weighted mean. The weights are our probabilities. So, before, kind of think about it like this. This is how we find a weighted mean. So we went through every x value, multiplied it by the weight, added them all up, divided by the sum of all the weights. So what I could do up here is think about, I'm going to take all my x values, but the weights I'm using are the probabilities that x takes on that specific value. So if those are my weights, in my denominator, I'll have the sum of those probabilities. But the sum of these probabilities should be what? If I'm adding up the probability of every possible outcome, this should be equal to 1. Dividing by 1 doesn't change anything, so I can essentially ignore it. So finding the mean or the expected value of a discrete random variable actually becomes a little bit easier than doing a regular weighted mean because I don't have to worry about the denominator. It's kind of like, I think I showed you an example similar to that when we were talking about like using midpoints. Instead of using frequencies, you could use the relative frequency, and then you don't have to worry about the denominator. It's the same idea, right? So if we're using probabilities as our weights, it becomes a lot easier to find this like weighted mean or the expected value of this distribution. Okay. I'll show you one other kind of idea here. Well, I'll show you the hard one and I'll show you the easy one. Okay. So I already talked about this. All right, so how would I find the mean number of new hires? Go through every x value, multiply it by its probability, add them up. So 0 times 0, plus 1 times 0.06, plus 2 times 0.03. Go through every single possible x value, add them all up, and I'm done. There's no denominator. Any questions on this process? Okay, I'm going to show you one more thing. Maybe some of you can help me out with this. I don't know. Maybe I'll show you a little. I'll do it on the board, and then maybe we'll do it in Excel just to kind of prove the point. So, one thing I always think is interesting is playing a lottery, right? So we kind of think about our different x values. We can see if you play a lottery, like a big, whatever the how they're called, Powerball or whatever, where there's like one major jackpot, right? So we'll just assume, kind of simplify the lottery. I know there's like intermediate prizes, but for us, we're just going to say maybe this is like playing like the big slot machines at a casino where there's just one gigantic prize. So you either play this lottery, right? You spend $1 on the lottery ticket and you lose, or let's say this lottery, the main prize is like $1 million. So I win $1 million. I paid $1 for the ticket, so my payoff, right, is $999,999. Okay? So if the probability that I win this lottery is really, really low, so let's do 1, 2, 3, 4, 5, 6, zeros and a 1, right? Which would make this what, 0.99999. Then basically what I'm doing, I can find the expected value of playing this lottery. That's really what we're doing here. It's just we have more than 2 outcomes, right? All I would do, I don't know how many, like in your finance classes, you do like expected return on investment of different projects, right? And you've got some outcomes that could occur and the different probabilities of them occurring. All you're going to do is go through, take your x value, right? Or the payoff of this investment of playing the lottery, multiply it by the probability that outcome occurs, and add that to the other possible outcomes, right? So the other possible outcome was that you win $1 million after spending $1 to play, and that probability was relatively low. So if we go ahead and compute this, right, this would tell us the expected value of playing a lottery. Right? You can like do this for yourself if you want. There was a point in time where I had like a table built out for this. So if we do this in Excel real quick, we would probably even find the cutoff. So there has, up until I believe it was 2017 or 18, the Powerball got to a certain level. If we compute this, well, maybe, why isn't it? There we go, let's me zoom in. So we've got our probabilities, our outcomes. So just putting those two payoffs of the lottery in. I said what, 0.0000001. So very unlikely, unlikely we win that lottery. I don't know why I copied that there. I didn't want to do that. So the probability I don't win is just 1 minus that. So now if I want to find my expected value, I'll take that payoff, multiply it by its probability, add that to the other payoff, multiply by its probability. And I find that the expected value of playing this lottery is actually negative. So the expected payoff from playing this lottery is actually that I lose money. So why am I playing it? Right? It doesn't make any sense. If I had any other investment and I said, okay, the expected value of this investment is actually 0. Do you still want to give me your money to put in these mutual funds or whatever it is? That would be like, what the hell? No, like, it doesn't make any sense, right? All right, but it's a lottery, and because we see this one big outcome, we think, oh, well, that would be great. Well, the expected value is actually still negative. Okay? Now, as this value grows, so maybe it's, I don't know, $100 million. So we could do, what would that be? So 99, 999, 999. Well, now you can see if that prize money gets big enough, the expected value actually becomes positive. So I would, if you really, I don't know, this is like the dorkiest thing to do, but if you were interested and you go out and you look up some lottery, they have to put out what the odds are, you can actually come up with the expected payoff for different lotteries. They've actually never been non-negative. So they're always negative. Otherwise, the lottery companies would go out of business, right? Where it would cost the state money. Except for there was one time in 2000, like I said, 17 or 18, where the payoff got so large that it actually was a smart choice to play the lottery because the expected value was like 0.001 or something. It was just barely positive. Right? But that's the same idea of what we're doing with these expected values, right? We're just taking the different outcomes, multiplying them by the probabilities, okay? All right, so if we can find the mean of a discrete random variable, we could also find the variance of a discrete random variable, right? It's going to be the exact same thing as a weighted variance without the denominator because our weights, probabilities, once again, the sum of the probabilities will be equal to 1. Okay? Standard deviation, same rules apply, just the square root of the variance, right? Nothing's changed there. So if we had this data set, right, we could go through, take that first value of 0, subtract our mean of 5.14, square it, and then multiply it by the probability we see x equals 0. Now you can imagine some of these, we're just wasting time, right? What do you automatically know this value is going to be? 0 times anything is 0. Like I could almost ignore this one, right? But I'm just kind of writing this out to be complete. If we actually had some, maybe we update our probabilities based off new historical data we get, then it'd be a little bit different. But I mean, this is the exact same process we use for finding a weighted variance, just without a denominator. Okay. So we go through every x value, subtract the mean, square it, and then multiply it by the probability we saw that x value occur. Okay. So if I gave you a small data set like this, all right, see how you guys were following what I was talking about earlier. I've got the different bonus amounts for this like crazy investment capital firm. This doesn't make a whole lot of sense, but stay with me, all right? You either get a bonus of 10 million, 6 million, 3 million, or $0, right? And each one of those bonus amounts has a different probability of occurring, okay? So with this information, right, what's the projected bonus amount for this individual in the upcoming year? So you can use these probabilities, use 4 different outcomes for X, and find the mean or the expected value for this, this bonus that this individual is going to get. So I'll give you a little bit of time to work on this. We'll kind of come together and talk about it. Try to reiterate. You want to work with the people around you. Don't feel like you got to be super quiet. Talk to the people around you. Try to kind of figure this out. We'll give you about 1.5 minutes, 2 minutes to do this. Okay. You've got 4 different bonus amounts, and I put 10, 6. They're all in millions, so you can kind of use 10, 6, and 3, and 0. Just add an m onto the n once you actually find the answer. So that's the x value you're interested in. You've got the associated probabilities there on the right-hand side. Go for about 20 seconds here at 3:30. All right. So if you haven't gotten an answer in yet, take your best guess here. So we got 23 of us. That's what we had before. All right, close it out. All right, so before we even start calculating this one, oops, there we go. If I looked at these values and I'm looking at their associated probabilities, if I had to guess kind of the range of where this mean, right, the expected value is, where would you say it's probably going to fall somewhere in between?
3 and 6.
Yeah, probably somewhere in between 3 and 6, right? I mean, it's kind of equally balanced on either side, right? 0.2 and 0.15 of this really large and really small value. 3 and 6 are the most likely outcomes. So remember, we're still finding a weighted mean. We're finding this expected value. So the values that will carry the most weight in influencing what that mean is are 3 and 6, right? So if I had to guess, I'd probably say it's somewhere between those two values. So I'm probably guessing C or D here. I mean, if it was in fact A, 250,000, how would these probabilities have to change in order for that to be the mean or expected value? Yeah, 0 would have to have a very high probability of occurring. 0.9, 0.8 maybe, something that was a lot higher than the third most likely outcome, right? Because in order for the mean to get that low, it would have to be being pulled down quite a bit by that 0 value. And here it's not even, it's the third most likely outcome, right? So it has the third most influence over the mean. So A doesn't really make, and probably B doesn't even make a lot of sense for the very same reason, right? We at the very least need 0 to have, probably a 0.5 or 0.6, probably to see an expected value or a mean as low as 1 million. Okay? So just the idea behind what we're doing, right? We probably can already narrow this down to these two options, right? From there, it's just, okay, I'm going to take each X value, multiply it by the probability it occurs, and then add them all up, right? We said it's the same as a weighted mean, we just don't have a denominator anymore. So I'll go through each X value, multiply it by the probability it occurs, write that number down, right? 6 times 6 times 0.25 is also 1.5. 3 times 0.4, what this would be, I think this is the 1.2. Then 0 times 0.2 is 0. Add these up. And I'm done. Okay. So, if it's helpful to create this additional column, that's fine. You can do this all in one line in your calculator, right? 10 times 0.15 plus 6 times 0.25, so on and so forth, right? That's as simple as the process is. We don't have a denominator to worry about. It's all we have to do, okay? Any questions on that one? Okay with that? So what if I asked you to find a variance? Okay. So quickly, just to kind of see where we're at going into this exam, the question I actually want you to answer right now is which of these answers can you 100% rule out? So I'm going to give you about 20 seconds to think about this, but which of these answers for the variance of the bonus amount can you rule out right away, right? So give you 15, 20 seconds, right, to think about this. You should be able to rule out one of these answers for the variance automatically, right? Remember what the variance is and how we calculate it. And one of these answers should be very clearly incorrect, okay? So go to 45 seconds here. So another 5 seconds or so. All right, I think we're missing one of you. So make sure you get an answer recorded. I think we had 23 people before. All right, there we go. All right, I'm gonna close it out. Right, which of these can I rule out right away? B, right? Why? It's negative. Remember, the variance always has to be positive because we're squaring those deviations, right? The lowest variation we can see in a data set is 0. There is no variation, right? From there, it's just increasing, right? Higher positive values of the variance represent that there's more variation in this variable. So we can rule B out right away. Right? I doubt that the variance is probably going to be exactly equal to the mean, but can't necessarily rule out 4.2. But from here, it's just a matter of kind of going through and calculating the variance, right? We remember we just found that the mean was 4.2. So we go through each X value, 10 minus 4.2, square that value, multiply that deviation squared by how likely is it we see that deviation? Well, 0.15, so we would multiply that deviation squared by 0.15. We would then add to that 6 minus the mean of 4.2 squared times 0.25. Go through that process for each of these four outcomes, right? And then that would give us our variance. So I think, and I don't think I have a slide for that, but right, you can imagine, if I wanted to write this out, it wouldn't be overly difficult. Right? We get what? 10 minus 4.2 squared times 0.15 plus 6 minus 4.2 squared times 0.25, I think it was. If I get none of these numbers wrong, let me know. Let's see if I can do this with memory here. 0. Okay. Just go through each X value's deviation from the mean squared multiplied by its probability of occurrence. I believe you get 9.96 if we enter this in your calculator. Yeah.
Do you not divide by the total number?
So we would divide by the sum of our weights here for a weighted variance, but the sum of our weights, since their probabilities will always be 1. Right? Exactly. Same sort of idea when we were doing the weighted variance or the expected value, or weighted variance, weighted mean or the expected value. we knew that we really didn't have a denominator anymore. Right? Yep. Yeah, so this almost becomes easier, right, than what we had to do before when we actually had, you know, frequencies or something where we actually had to divide by the sum of the weights. Right? Questions on that? All right. So I had these, but I think I'll save this for Wednesday. We'll end class on this kind of an interesting example on Wednesday. I want to introduce the idea of binomial distribution, so we don't have to kind of start with that on Wednesday's class. So what we're going to do with binomial distributions is it's a specific type of discrete random variable. Right? So if we have these certain criteria met, we know exactly what the probability mass function is going to be. Up to this point, the probability mass function, I'll come back in just a second, right? It was actually like this weird function where we were just told the probabilities. There was no like functional form. We couldn't write out what the function actually is. So what we can do with a binomial is have an actual equation. So anytime we have an experiment that we're running over and over again, so we run it n number of times. N is the number of trials, the number of times we run this experiment. It has to have only two outcomes. We'll call this success failure. If you want to think about it like binary, it's a 1 or a 0. You know, if I'm flipping a coin, I either see heads or tails, right? There's two outcomes. Any one trial, the probability of success is the same across all of them. So if I flip a coin, right, we talk about the independent events, the probability is 0.5 on every coin flip. Where there's a lot of other situations where if the probability of success on any one trial is consistent, this also has to be met. We know that we're looking at a binomial distribution. So two outcomes, the outcome of the success is the same across all trials. We're running that experiment n number of times, right? We're going to have a binomial distribution or a binomial variable, random variable. Okay? And we have to make sure the trials are independent. This one, I'll never kind of give you an example. I'm trying to trip you up from this, so we don't have to worry too much about the fourth one. So we might then be interested, okay, if I flip a coin 100 times, what's the probability it comes up heads 50 of the 100 times? Or what's the probability it comes up heads 100 out of 100 times? So we've got this number of trials, and what we're interested in finding the probability of is going to be different number of successes. So what's the probability this random variable x, you know, is equal to 50? We get 50 successes out of maybe 100 trials. So we can identify these three pieces of information that we're going to need: that probability of success on any one trial, and the number of trials that we've run, and then x is the number of successes we're interested in finding the probability of. We're then going to have this probability mass function that looks something like this. So what are we on time? We got another minute or two. I might go, yeah. So finish class out with this, right? We'll kind of pick back up using this equation. But one thing I want to bring up that we probably recognize everything that's in this equation, right? We can take things as powers. The one thing we might not recognize is this factorial. So all a factorial is, does anyone know what a factorial is? That's that exclamation point. So if I have 5 factorial, anyone know how to do that? Yeah.
Is it 1 times 2 times 3 times 4 times 5?
Yeah, I usually say start with a number next to the exclamation point and then multiply down to 1. I think that's an easier way to kind of think about it. But yeah, that's essentially the idea. So we'll be using these factorials next class. We're going to dive into the binomial distribution. I expect you to watch that video I'll put up on YouTube by next class. It kind of covers the Poisson distribution. Other than that, I'll see you guys on Wednesday.